Hey students, I thought I'd make another video solution here. This one is also out of chapter 13, but it's from the harder book. So it is the volume 2, chapter 1 of the university physics books, and it's number 60, and it says this: show the relationship between alpha and beta. And so just as a quick review, if you kind of remember here, if we had something of length, it doesn't matter what the material is, but I'll just say aluminum. And recognizing that this rod is made out of a bunch of aluminum atoms, when you heat it up, and so if the temperature goes from some initial to some final, delta T, the molecules are going to move faster. They're going to bump into each other, and because of that, this object is going to need more space. It's going to grow. We call that a thermal expansion, or maybe I'll call it delta L. And so L is its original length, and now it's going to get a little bit longer. And so what we like to say here is that the new length, I'll say L final, is how long was it before plus this little increase. And this little increase, we like to say, is proportional to the temperature. In other words, if the temperature goes up 1 degree, it grows by a certain amount. And then 2 degrees, it doubles and triples. And so the point is this delta L would depend upon delta T and some proportionality constant. And this would technically do it for every meter. And so if we had a bunch of meters tied together, each meter would grow by the same amount. And so that way the total growth of this rod depends on 2 factors, well, 3 factors. But this one right here is a double per, if you will. This alpha is how much does it grow for each meter for each degree, okay? And so that's what the alpha means. Now, the beta is a 3-dimensional, and you might even say more realistic approach, because when you warm up something like a cube, and that's how they suggest we do this, it will get bigger in its width, it'll get bigger in its height, and it'll get bigger in its depth. And so the same idea is going to happen where there is going to be a change in the volume. There's going to be an increase in the volume. That is, we can say the final volume, the volume after you warm it up, okay, is then the initial volume plus this change in volume. And the same idea applies here, that this change in volume is going to be proportional to the temperature change. That is, if you warmed it up 1 degree, well, it increases by a little bit. But if you warm it up 2 degrees, it warms up twice as much, and 3 degrees, 3 times as much. And that proportionality constant is referred to as a beta. Now, again, this is warming per volume. And so if I had a stack of these cubes, then this volume increase would be times the volume, because each little cube would increase by the same amount. In other words, beta is the change in volume. It's a double per again. It's the change in volume for each cubic meter for each degree. So the total change would take this double per and multiply by your 2 factors. It's like saying it costs $200 to go to Hawaii. Wow. Well, it's $200 per person. Oh. Well, that's still not bad. Well, it's $200 per person per night. So if you want to know how much it goes to Hawaii, you have to take that $200 per night, you have to multiply by the number of people going, and you have to multiply it by the number of nights. That's a double per, and that's what these are. And so these double pers, this is how much does it increase per meter for each degree. This is how much volume does it increase for each cubic meter each degree. Anyways, I hope I didn't bore you with kind of a little lecture review here, but that is what the alpha and the beta are, okay? And so our job is to show that they're connected. And it kind of makes sense that if something grows in length, like back here, it's also going to be doing the same thing in its height and its depth. And so it's not a surprise that mathematically there is a connection between its volume and its height. And in fact, I printed up the table. It looks like it's table 1.2. So this is out of the university physics book. But you can see that, and I'll just, I was talking about aluminum, so let me pick on aluminum. You'll see here, this says the linear coefficient. So this is the alpha. And they have it as 25 times 10 to the minus 6. And this is the volume. This is the beta. And you can see that it is 3 times bigger. I'll pick on copper, too. Copper is 17. You multiply 17 by 3, and you get 3051. And sure enough, well, there it is. I skipped over brass. I'm not real sure why. It is pretty close. Let's see, 19 times 3 would be 57. So probably some rounding here. Maybe this is really an 18-point high. And so it doesn't quite round up to 57. But again, it's just 3 times more, other than some rounding. Here's another good one, right? 12 times 3 is 36. 14 times 3 is what, 42? Yep, sure enough. And this was close, 36. 9 times 3 is 27, or this is 0.9 times 3, so it's 2.7. Anyways, I'll stop there. But you can see that it's very evident from, I'll call this experimental data, that it's 3 times. All right, well, let me jump into the problem then. And so let's do our little proof. And they suggest using a cube. So I'll draw this little cube again here. It says infinitesimal change dV of a cube with sides of length L and is increased by a temperature of delta T, or dt. So I'll go ahead here and say, all right, I have a cube. And let me give it, or try to give it, a 3-dimensional depth. Here's its height. So here is its width, L. Here is its depth, L. Here is its height, L. And as I was drawing earlier, if you warm it up, it's going to expand, and I'll exaggerate, a little value, delta L, because of its width. It's going to get a little taller because it's going to, again, expand a delta L in its height. And it's going to go back into the 3-dimensional plane here. So its depth is going to be another delta L. And so its volume now looks something like this. It's a little taller, a little wider, and a little deeper. So its volume before was L cubed. Its volume after I warm it up would be this L plus delta L cubed. And if you let me come back to the little mini lecture here, this delta L is alpha L delta T cubed. Which then, if you factor out an L, has this 1 plus alpha delta t cubed. And so I'll factor out an L and, of course, cube it. Okay, so this, well, let me do a little more math. It could look something like this. It's L cubed. And this looks like an A plus B cubed. And maybe I should kind of remind you of your binary expansion here. But this would be multiplied out in a sequence of terms where we can group them in the powers of A and B, but the powers have to add up to 3. And the coefficients are part of Pascal's triangle. And so here would be the coefficient for A plus B squared. This is the coefficient of AB. So starting there, then this is the square, and then this is the AB cubed. So the coefficients here would be a 1, a 3, a 3, and a 1. And if it's been a while since you've done your binaries, you can, just multiply this out. Just, do A plus B, and do your FOIL. So you get A squared plus AB plus BA plus B squared, which comes out to be A squared plus 2AB plus B squared. And then take that and multiply it by another A plus B, and you'll get this. All right, so there might be a lot of work there. Maybe I should have done it with a little bit of calculus. In fact, maybe that's what they were implying when they say differential. Yeah, they probably were. So let me do that method also. But I'll keep going down this road. Here's what I wanted to say is, looking at this first term, this would be the first one cubed, the second one raised to a power of 0 times 1. So that's just 1, because 1 cubed is 1, and alpha beta raised to a power of 0 is 1 times a 1. And then this next term would be 3. And then we would have the first term squared. 1 squared is just a 1. And then we would have alpha times delta t. The next term would be the 3 for the coefficient. And it would be alpha to the 1 power, so it'd be a 1. And then you would have your alpha squared and your delta t squared. And the last term would have a coefficient of 1. And an A raised to a power of 1, and then alpha cubed delta t cubed. All right, so this is the mathematical equation for the new volume, if you will. But if you look carefully at this, the first term, when you multiply it out, is, calling this volume, is the initial volume. The second term then is 3 times alpha times the initial volume times delta t. The next term is 3 alpha squared initial volume temperature squared. And the last term would be alpha cubed initial volume delta t cubed. But keeping in mind then that final volume is initial plus the change, these 3 terms are the delta V. These are the 3 that represent how much did it change by. Okay. And let me call this page 2. And so I really have a delta V equals, and that first one here is this 3 alpha initial volume delta T. And then let me just go dot, dot, dot. Let me not even write these. And here's why. As I look at these, what I'll call higher order terms, I have alpha squared and alpha cubed. And I come back to this chart and I look at any of these alphas, and I'll just pick on aluminum. I've got 25 times 10 to the minus 6. Now, I suppose you might want to call that just 25 times 10 to the minus 5. But when you ask me to say square that, this becomes 10 to the minus 10th. And of course, 25 squared is 625. But notice that this number squared, this alpha squared, is 10 to the negative 5 times smaller than just the alpha. Now, 10 to the 5, or 10 to the minus 5, is 100,000 times smaller. And if you were to ask me to cube it, this would be like 10 to the 15th. And then we would have like another 12 or 13, 14 in here somewhere. But this is even ridiculously smaller. And my point is, then this term is 100,000 times smaller than this term. And this term is another 100,000 times smaller than this one. And both of these, then, are so incredibly small for any of these realistic numbers that I could justify saying that the change in volume is really this much, plus things that are so incredibly small, they just really don't matter. They're just what we call insignificant. And so that's why I'm just going to put a dot, dot, dot and say, I don't even need to worry about all those other terms. They're just insignificant. So that reduces my equation of delta V to something very manageable. And then when I compare it to my little mini lecture here, delta V, the stuff in front of volume and delta T. So here's volume and delta T. And the stuff in front, which is 3 alpha, must be the beta. And so there's my proof that beta is 3 times alpha. Ta-da! Now, if you're still hanging around, you might do something like this also. Because your author says, do it. And I think he kind of implies some calculus here. So you might do this. You might say the new volume, we'll call it V final, is equal then to the original volume plus the delta V. And the length, okay, so the length, and here I'll just maybe talk about the width of the cube, is the original plus alpha times original length times delta T. And so you could probably write the final volume as the initial volume plus alpha initial length T cubed. And if you do this, well, let me factor out the L first. And so if I factor out the initial and cubic, I get this 1 plus alpha delta T cubed. And of course, what I'm doing is no difference than what I did back here. But where I am going to make a slight difference is maybe right from the beginning, I will call that the initial volume. And I will then also say, doing infinitesimal changes, I might do a little bit of calculus here and say, all right, this is my dT. This is a small change in temperature. Okay. See, if I then come over here and say, okay, so the new volume is this old volume times this. And I do something along these lines and say, all right, let's look at dv dt. That is, let me take the derivative of the volume with respect to temperature. I would then have this original volume. And when I take the derivative of this, I bring down the 3, and then I get 1 plus alpha dt cubed. I'm sorry, squared. And then the chain rule gives me an alpha. And so this then, let's see if I'm saying this well, has a rearrangement, I guess, of my 3 alpha. I have my original volume, and I've got this little factor of how the temperature changes. But I would then rewrite this by moving the dt to this side. But I could then argue that this is an infinitesimal change in the volume times some factor that then is related back here to the change in temperature, but that's that additional factor. So that's the 3 alpha. I like this one a little better. It kind of kept me away from too much calculus. But I did think that perhaps maybe that's what the author was implying. Anyways, either way, this must be the beta. This is the factor out in front of the other pieces that say, hey, what is the volume? What is the change in temperature? And in this case, a small factor that we could argue this is so small. I should have said that it's really just essentially a 1. And so this is the volume times the dt, and then this is the factor out in front. So whichever method you like better, this is the proof that I think they were looking for. All right, take care.